I'm going to describe how we analyze data obtained from a plug flow reactor where we have a catalytic reaction, and the reaction is going to be modeled by a Langmuir-Hinchwood mechanism. So the system is a gas phase reaction where A plus B goes to 2C, and the virtual catalytic reactor lab that we use to generate the data, the link is given here. The spreadsheet, which I am showing a snapshot of, and let me expand the part that we want to initially look at. 3 kinetic parameters we want to determine, a rate constant and 2 adsorption equilibrium constants. The way the reactor is run, experimentally we change the pressure of the reactor and the 2 inlet molar flow rates of reactants and measure the outlet conditions. We're going to then numerically integrate the mass balances using fourth order Runge-Kutta, and this part of the spreadsheet uses a constant step size of 0.05 cubic centimeters for a 10 cubic centimeter reactor. So let's look at a spreadsheet in the various sections in the spreadsheet to better understand how we carry out these calculations. Well, here's the spreadsheet. So first let me point out that the mass balances that we're using, the equations are shown here on this worksheet, as well as the terms that were used in the fourth order Runge-Kutta solution. The nomenclature used in the spreadsheet is presented here, and then a detailed explanation of how to use the spreadsheet, because we go through a number of steps. Won't go through each of these steps. I'll go through some to give you an idea of what's involved. And so here's the calculations. If we input values into the yellow cells for reactor conditions, inlet flow rates, and the pressure, we can then integrate those differential equations, the mass balances, and determine the outlet parameters if we pick constants for the rate expression. And I show the results of the nonlinear regression here, but essentially these constants in green are then the ones that are used to carry out this numerical integration. Well, in order to do the nonlinear regression, we need to repeatedly solve these differential equations for a number of different conditions so we can then compare the experimental measurements, in this case experimental means from a virtual laboratory, to the values that we calculate for the parameters that we input. And of course initially we have to make guesses as to values. The actual values that are used to generate the original data in the virtual laboratory are shown in these grayed out boxes. Of course, if you are using the virtual catalytic reactor, you won't know these values. That's what you're trying to determine. So they're included here to give you an idea for 20 measurements how close we get to the actual values. So these nonlinear regression results you can see are reasonable good for at least KB and rate constant K. So the way we do this repeated integration is to use data tables. And the way data tables work is we create, in this case, let's look at just this one data table. We have a number of different values for the molar flow rate of A into the reactor and the pressure. And so the way the data table works, and there are spreadsheets that explain data tables in detail, it will input into those feed conditions the molar flow rate of 0.1 for A, and molar flow rate of B is kept constant 0.5, and for pressure 0.3, it will solve the differential equations and then calculate what's the molar flow rate. So this is 0.059 is the molar flow rate of A leaving reactor. 0.459 is the molar flow rate of B leaving reactor. And so this table represents 24 times where we go through this numerical solution of the differential equations and generate the molar flow rates out. Below it are 2 more tables where now we keep the molar flow rate of A constant and vary the molar flow rate of B. And again, we have 24 values for different flow rates. Well, we're only going to use some of those values, and we use some of those values, created a table down here, where the yellow shows the experimental measurements that we obtain from this virtual reactor for flow rate of A leaving reactor, flow rate of B leaving reactor. And then what we've done is read values off of these data tables and insert those values here. For example, flow rate of A and B at 0.5 and pressure 1. And that corresponds to, if I can go back up, 0.189 molar flow rate of A. That's the value that's entered into the table for the calculated value. And of course, you can see it's very close to experimental value since we've done the nonlinear regression. And likewise, we generate this series of values for a flow rate of A, flow rate of B. We then calculate the residuals, how much the calculated value differs from the experimental value. We take the square of those residuals for both the flow rate of A and over here flow rate of B, and then we add them all together, and then we sum this AA column to get the sum of the squares. This is what we minimized by going into Solver. So in Data, Solver. So we're minimizing that sum of squares. We change those three kinetic parameters, and I've named them in the spreadsheet, so that's why we can show their names. And we make the variables non-negative, so we only can have positive values of the K values. When we hit solve, it generates the answer that we have. The rest of the spreadsheet then generates the confidence interval, and details of how to do this confidence interval are contained in other spreadsheets. And to not make this too long, just point out that we essentially approximate partial derivatives. So this X matrix, or how the molar flow rate of A leaving the reactor, FAF, depends on these three parameters, and we do that by taking the base values, these are the values from nonlinear regression, making slight variations of them and seeing how much the flow rate changes. So we approximate the partial derivative as finite difference ratio. And then we calculate this matrix that is used in the parameters, and I won't be able to go into all the details here, but the idea is explained in other screencasts. The three yellow boxes correspond to the three values from this matrix that are used in the calculations to get the confidence intervals, which are expressed here. So these are 95% confidence intervals. So it's a spreadsheet that takes some time to understand the aspects, and that's why I included this detailed step-by-step way to use the spreadsheet in order to calculate kinetic parameters and their confidence limits.